point, you guys, we've been foiling to get quadratic functions and then factoring to solve quadratic functions. Today we're going to graph a quadratic function. And the first thing I like to point out is the standard form of a quadratic function, which is in the box right here. It looks just like the standard form that you've seen before, with coefficients a and b, and the constant c. So now we're going to go ahead and graph it. And we've already completed the table for number 1. Go ahead and graph the parent function, y equals x squared. And we call it a parent function because all other functions we're going to graph today are based off of this function, meaning this is the parent. All the other functions are its kids. All right, so graph it. Well, right off the top, you can see that we only have half of the graph. So what we need to think about is what happens if you were to have plugged in negative values? Coleman.
It would have had the same output.
Yes, the output would be the same because when you square a negative, you get a positive. So quadratic functions are symmetric about a vertical line. So if I were to jot in a little vertical line, and then I found the graph's mirror image, meaning, okay, this point would be over 1, this point would be over 2, up 4, this point would be over another one, and then up to 9. And I use that line of symmetry to get the other half of the parabola. So I just used some words right there. I use the fact that this is called a parabola. The graph of a quadratic function is called a parabola. And I also use another word, that this is the axis of symmetry. Excuse spelling. You would know that the special word for this point, this one right here, I don't know if you can see where I'm pointing.
Vertex?
Ah, thank you for raising your hand next time. But yes, that's called the vertex. And for the parent function, the vertex is always at 0, 0. The vertex is always at 0, 0 for the parent function. And for the parent function, it's symmetric about the y-axis. Does anyone know another name for the y-axis? If I were to write the equation of the line of the y-axis, what would that equation be? Kiani?
X equals 0.
Perfect. About the line x equals 0. Therefore, the axis of symmetry, the vertical line for the parent function, the line that divides the parabola in half, is the line x equals 0. This is the axis of symmetry.
Wait, what does it say above the graph?
All right. Now for the next thing, I'd like you to find what I'm going to call my delta y. And delta means change in math. So look at your y column, and I want you to find the difference between 0 and 1. And you don't really have to find it, you just know it to be 1. What's the difference between 1 and 4? What's the difference between 4 and 9? When you're looking at the delta y, does 1, 3, and 5 follow a certain pattern? They're all odd numbers. So if you were to find x equals 4, without having to plug in 4, what would you expect the next number to be? Anna?
The next number would be 16.
The next number would be 16, because if you add 7 to 9, you'd get 16, and also if you squared 4, you'd get 16. And if I had to find the next one, you'd expect to add 9 and get 25. Well, it turns out that all quadratics follow this delta y pattern. So let's look at it on the graph next. I'm going to use a different color. If I go over 1, I go up 1. You see where I'm marking? If I go over another one, I go up 3. If I go over 1 again, I go up 5. And that pattern can continue for till infinity. Over 1, and you go up according to the pattern. You always go over in one direction, though. So go ahead and turn the page. And we're going to see what happens when the graphs start to look a little bit different. So let's graph the parent function. So we start at the vertex as 0. The parent function is y equals x squared. Let's graph the parent function, instead of thinking about the table, I want you to think about over 1, up 1, over 1, up 3. I'm going to go from the vertex, over 1, up 1, over 1, up 1, 2, 3, over 1, up 1, 2, 3, 4, 5, over 1, up 1, 2, 3, 4, 5, 6, 7, and that's all the dots that will fit on the line. Now make your parabola by curving the lines together and an arrow on the side. And then to get the other half, we're going to find its mirror image. And plot that. There is the parent function, y equals x squared. Well, what happens when the parent function gets a coefficient of the x squared term, when it gets an a term? Well, it's interesting. If you plugged it in, you went 0 squared is 0, times 2 is 0, meaning the vertex is still going to be at 0, 0. But now if I go 1 squared is 1, and then I double it, I get 2. 2 squared is 4, and I double it and I get 8. 3 squared is 9. I double it and I get 18. Well, let's find the delta y's now. So now I have 2. What's the difference here? What's the difference here? 10. Well, my delta y's before were 1, 3, 5. I'm sure you guys can see the relationship between my new delta y's. So for the graph y equals 2x squared, your delta y pattern is the a value times 1, the a value times 3, the a value times 5, the a value times 7, etc. And the vertex is still at 0, 0 because all we're changing is we're adding an a. So I'm going to choose a different color. I'm going to do this in blue. It has the same vertex. I'm going to graph my new function of 2x squared. Start at 0, 0. And instead of going over 1, up 1, I'm going to go over 1, up 2, over 1, up 6, over 1, up 10, and if I had room, I'd go up to 14. Okay? So if my a is 2, all I'm doing is doing 2 times 1, 2 times 3, 2 times 5, 2 times 7. Starting at the vertex, over 1, up 2, over 1, up 1, 2, 3, 4, 5, 6. I hope I made it. Over 1, up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Woo! And that's all I have room for. And I apologize for my my hesitance. I have a hard time staring into my tablet and counting the lines. Alright, so now we're going to do the same thing over here. And let's see. And one more over there. So now let's just do, who can tell me what they think the delta y pattern would be for 3x squared? I only got one hand up. Only one person thinks they can anticipate what the delta y pattern would be if a was 3. Katie, what do you think?
3.
Okay.
9.
Nice.
15.
Great.
And 21.
Perfect, etc. Meaning you'd be going 3 times 1, 3 times 3, 3 times 5, 3 times 7. Nice. So let's add that one later, and let's jump to negative 2x squared and see what happens when our a value is negative. So just down below here we have our new function, y equals negative 2x squared, and let's find the delta y pattern. So if we know it's 1, 3, 5, but now we have to multiply it by our a, and our a is negative, now our new delta y becomes negative 2, what's next? Negative 6, then negative 10. Negative 2 times 1, negative 2 times 3, negative 2 times 5. And for all of these, once again, we are starting at 0, 0. I'm going to choose red this time. My vertex is still 0 for the parent function. All I'm doing now is seeing how this negative a affects my graph. So I'm going to go over 1, but instead of going up 2, I'm going to go down 2 because it's negative. I'm going to go over 1, and then I'm going to go down 1, 2, 3, 4, 5, 6. I'm going to go over 1, and I'm going to go down 18, or 218, down 10. Okay, think about the axis of symmetry is going to be that y-axis. Find the mirror image. There's my graph, my parabola, for y equals negative 2x squared. So we can notice several things. First off, for these values of a, what happens to the graph as the absolute value of a gets bigger? I mean, we've only done 2, but compared to the parent function, what happens to it? Yes?
The graph gets smaller.
Yeah, it gets skinnier. So as a gets bigger, as the absolute value of a increases, the graph gets skinnier. Now, also, who can take the absolute value of a is greater than 1? What does that mean? What kind of numbers are we dealing with? Ingrid?
Positive?
Well, the absolute value. They could be negative, but if the absolute value has to be greater than 1, what type of number? Are we dealing with decimals?
Whole numbers.
Dealing with whole numbers. So basically, for this pattern, we're not dealing with fractions right now. This page, if you had a fractional value of a and you wanted to have help doing your homework, you wouldn't look back at this page. All right, so now let's generate a rule. You have a reflection in the x-axis, and it's called a vertical stretch. We're just going to stretch the graph up and down, which makes it skinnier. And to get the delta y pattern, you go a times 1, a times, 3, a times 5, a times 7, etc. I know I skipped a couple. You can go back and do those later. Any questions? All right, let's go to the next page. Notice what is changing. Notice what's changing, you guys, is that the absolute value of a is less than 1. So now we have fraction-y values of a, or a is a fraction. And at first glance you think, oh gosh, I have to multiply a fraction times 1, a fraction times 3, a fraction times 5, and we're going to have to deal with fractions. Oh no. Well, it's actually not so bad. Let's start with this one, actually, okay? Let's start with 1/2 x squared. We know, because of the parent function, that our vertex is going to be at 0, 0. So for this function, let's go ahead and calculate the delta y pattern. Okay? So delta y would be, let's see, 1/2 times 1, 1/2 times 3, 1/2 times 5, 1/2 times 7. And for the most part, I always tell you guys to leave your answers improper, but for some reason, I think it's easier to use this method when you write them as mixed numbers. So I'm going to simplify it down here and say 1/2, 1.5, 2.5, 3.5. Are you ready to go? Put your first dot at the vertex, at the origin for your vertex. You're still going over 1, but now when I go over 1, I'm going to go up 1/2. And I just put a dot, kind of halfway. This is kind of, it's an estimate. Now from there, I'm going to go over 1. I have to, and I'm supposed to go up 1.5. So I'm going to go up the half, and now I'm on a clear number, and then go up another 1, and I end up there. Any questions on how I got that second dot?
Yeah.
So from here, I went over 1, I went up a half, and then up the 1.
Oh,
Now I'm going to do it again. I'm going to go over 1, but I'm going to go up 2 wholes and a half. Whoops! Ah! If I had to do it again, I'd end up back on a whole number, right? Okay, so connect your dots. And let's go ahead and do the mirror image on the other side. And connect the parabola. My graph got kind of funky right here. That's the graph of 1/2 x squared. And if you were filling this in, 1 squared is 1.5, that would be a half. 2 squared is 4, a half is 2. 3 squared is 9, a half is 4.5. You could, and the table points are still applicable. You could go over 3 and then go up and see that you have a point at 4.5. But using the delta y pattern is faster. Trust me. Okay, let's do another one. Let's try this one. Okay, let's write it down below. Y equals negative 1/3 x squared. So now when I'm doing my delta y pattern, I'm going to have negative 1/3 times 1, negative 1/3 times 3, negative 1/3 times 5. Okay? I'm going to write the pattern over here because I'm running out of room. Negative 1/3. Ooh, look, the next one's going to be a whole number, right? Negative 1. Negative 1 2/3. Negative 2 1/3. I think it's easier when you do the mixed numbers, so I think that's what you should do. Okay, so the parent function is x squared, so our vertex is at 0, 0. Put your vertex. The first thing says to go over 1, down 1/3. So you kind of estimate. Down 1/3 is not very far down. Okay? Then the one after that says go over 1 and then go down a full 1. So I put my dot about 1/3 of a way below the next crossing point. But then here in this third one, it gets easier because this one wants us to go down 2/3, so back to back to a whole number, and then down a whole other one. Everybody see how I got that last point? So I went over 1, down 1/3, over 1, down a whole 1, but I'm still under 1/3. Then I went over 1, down 2/3, and then a whole 1. Now I'm going to go down over 1, down 2, and a little bit. So there's my graph. And mirror image on this side. And you guys are not going to be exact, but they're going to be close enough. And notice that when the a value is negative, and we noticed this on the last time, the graph opened what direction? When it opened up, wasn't a positive? And then when it opened down, a was negative. All right, I think you guys should recognize that. So this we call a vertical shrink because it gets less steep. And still, the delta y pattern you get by going a times 1, a times 3, a times 5, etc. Okay, we're on the last page today. Now we have the parent function, and luckily there is no a value, right? So we're not going to have to multiply 1357. We're going to use 1357. But we're going to have to translate. We're going to do a vertical translation. Go ahead and graph the parent function. Over 1, up 1, over 1, up 1, 2, 3, over 1, up 1, 2, 3, 4, 5. All right, so there's the parent function. What do you guys think is going to happen when you add 2? Where's the vertex going to go? Tate.
Positive 2.
Yeah, it's going to go up 2. So instead of the vertex being at 0, 0, now our vertex is going to be at 0, 2. So our first point, our vertex for y equals x squared plus 2 is at 0, 2. It's a vertical translation. We're translating the whole graph up 2 units. So now that we know our vertex starts 2 units up instead of at 0, we're going to repeat our delta y pattern. Over 1, up 1. Over 1, up 1, 2, 3. Over 1, up 1, 2, 3, 4, 5. Then find the mirror image. Ooh, my graph got a little shaky. All right, what do you think is going to happen when we are subtracting 5? Where's my vertex going to end up? See, the parent function is going to move up or down. Eli? It's going to move down 5. So my vertex will be at 0, -5 for y equals x squared minus 5. So now, from 0, 0, go down 1, 2, 3, 4, 5. That's your new vertex. To get the graph, there is no value of a, right? We're still graphing y equals x squared, so we don't have to multiply 1, 3, 5 by anything. Go over 1, up 1. Over 1, up 1, 2, 3. Over 1, up 1, 2, 3, 4, 5, etc. Now, you guys spent all last night making tables. I think 2, 3, 4, 5. Hope we got that last one right. I think that this method is less time intensive once you get the hang of it. Okay, so how do we take care of the upward, downward, vertical translation? The vertex will always be at 0, c. So if c is positive, you'll go up, and if c is down or negative, you will go down. All right, so I'll take your question in a second. I'd like you guys to, with the time remaining, take a look at the practice problems on page 5.